Welcome to this tutorial on debugging pods in Kubernetes. When working with containerized applications, you'll inevitably encounter pod failures and issues. Understanding how to systematically identify and resolve these problems is a critical skill for any Kubernetes administrator or developer. In this video, we'll explore the most common pod issues and learn practical solutions to fix them quickly and effectively. Before diving into specific problems, let's establish a systematic approach to debugging pods. First, always check the pod status and events using the describe command. This gives you immediate visibility into what's happening. Second, examine container logs to understand application-level errors. Third, verify that sufficient resources like memory and CPU are available. Finally, validate your configuration including image names, environment variables, and volume mounts. Following this sequence helps you quickly pinpoint the root cause of most issues. The first step in debugging is to gather detailed information about your pod. Use kubectl describe pod followed by the pod name to see comprehensive details including events, conditions, and error messages. For a more structured view, use kubectl get pod with the -o YAML flag to output the complete pod specification. These commands reveal scheduling problems, image pull failures, and configuration errors that prevent your pod from running correctly. Pods can enter several problematic states that indicate specific issues. The pending state usually means Kubernetes cannot schedule the pod, often due to insufficient resources or scheduling constraints. CrashLoopBackOff indicates that your container starts but immediately crashes, and Kubernetes keeps trying to restart it. ImagePullBackOff means Kubernetes cannot retrieve your container image from the registry, possibly due to authentication issues or incorrect image names. The error state shows that the container terminated with a non-zero exit code, indicating an application failure. Container logs are invaluable for understanding application behavior and errors. Use kubectl logs followed by the pod name to view output from the default container. If your pod has multiple containers, specify which one using the -c flag followed by the container name. To see logs from a crashed container, use the -- previous flag. This shows logs from the previous container instance before it failed, which is crucial for diagnosing crash loops. Resource problems are among the most common causes of pod failures. When a container exceeds its memory limit, it gets killed with an OOMKilled status, meaning out of memory killed. CPU throttling occurs when your container hits its CPU limit, causing performance degradation without actually terminating the pod. Pods can remain in pending state when nodes don't have enough available resources to accommodate them. Storage issues arise from volume mount failures or when the container fills up its allocated disk space, preventing the application from functioning properly. Sometimes you need to interact directly with a container to diagnose issues. Use kubectl exec with the -- at flags to execute commands inside a running container, such as opening a bash shell. This lets you inspect files, check processes, and run diagnostic commands in the container's environment. For more advanced scenarios, use kubectl debug to create an ephemeral debug container attached to an existing pod. This is particularly useful when the original container lacks debugging tools or has crashed completely. Configuration errors are frequent culprits in pod failures. Typos in image names or incorrect registry paths cause ImagePullBackOff errors. Missing or incorrectly referenced secrets and ConfigMaps prevent your application from accessing necessary credentials or configuration data. Invalid environment variables can cause your application to fail during startup. Misconfigured liveness or readiness probes lead to Kubernetes repeatedly killing healthy containers or routing traffic to containers that aren't ready, creating cascading failures across your application. Network problems can be subtle but devastating to distributed applications. Service discovery failures occur when pods cannot resolve DNS names for other services, breaking inter-service communication. Network policies may inadvertently block legitimate traffic between pods or from external sources. Port conflicts happen when multiple containers try to bind to the same port on the host, or when port specifications don't match between your pod and service definitions. Ingress configuration errors prevent external users from reaching your application, often due to incorrect routing rules or missing backend services. Let's wrap up with some best practices for effective pod debugging. Always start by checking events using the describe command, as they often contain the exact error message you need. Proactively monitor resource usage and set appropriate requests and limits to prevent resource starvation and OOMKilled situations. Use restart policies strategically, choosing always for long-running services, on failure for batch jobs, and never for debugging scenarios. Finally, implement proper health checks with liveness and readiness probes to catch issues early before they impact users. By following these practices and using the systematic approach we've covered, you'll be able to quickly diagnose and resolve most pod issues in your Kubernetes clusters.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.